Problem B2. Part A. A spherical region of space of radius r has a uniform charge density and a total charge positive q. An electron of charge negative e is free to move inside or outside the sphere under the influence of the charge density alone. For this first part, ignore radiation effects. Question 1. Consider a circular orbit for the electron where r small less than r big. Determine the period of the orbit t in terms of any of all of r small, r big, q, e, and any necessary fundamental constants. Question 2. Consider a circular orbit for the electron where small r greater than big R. Determine the period of the orbit t in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Question 3. Assume the electron starts at rest at r small equal to r. Determine the speed of the electron when it passes through the center in terms of any or all of big R, Q, E, and any necessary fundamental constants. Part B. Accelerating charges radiate. The total power P radiated by charge Q with the acceleration A is given by formula P equal C xc a power n, where c is a dimensionless numerical constant which is equal to 1 over 6 pi. C is a physical constant that is a function only of the charge q, the speed of light c, and the permittivity of free space epsilon 0, and the n is a dimensionless constant. Determine C and n. Part C. Consider the electron in the first part, except now take in account radiation. Assume that the orbit remains circular and the orbital radius small r changes by the amount absolute value for dr much less than small r. Question 1. Consider a circular orbit for the electron where small r less than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. Question 2. Consider a circular orbit for the electron where small r greater than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. Solution for Part A. Question 1. Consider a circular orbit for electron where small r less than big R. For this case, we need to take into account only charge which is inside of a sphere with radius small r, because for other charge, due to Gauss theorem, we have no influence inside of such shell for what is inside of this shell. So it means that we have to count what is the charge of this small sphere with a radius small r. Charge of such a sphere will be proportional to small r cube, which is q multiplied by small r cube over big R cube. In this case, we have force between this sphere and our electron, and force between electron and this small sphere equal this expression. Now we can count what is the speed. We have centripetal force, which is mv square over small r, equal to force from this small sphere with radius r. And from here we can find what is the speed. Speed equals this expression. And finally we can count what is total period. Total period will be 2 pi small r over speed v, which is equal to this expression. That was the answer for question 1. Question 2. Consider a circular orbit for the electron where small r greater than big R. Now we have sphere with a total charge q, and the force will be just a regular force between point charges q and e, which is this one. Again, we have mv square over r equal this force, and from here we can find what is speed. That will be this expression, and again we have period equal this expression, which is like third Kepler law, where square of periods proportional to cubes of radii. And for the first question we have time is not depend from radius, like for simple harmonic motion. Question 3. Assume the electron starts at rest at r equal to big R. Determine the speed of the electron when it passes through the center in terms of any of all fundamental constants. Here we just need to integrate the path, because we know what is the force. We have kinetic energy mv square over 2 equal integral from 0 to 2 big R from force, which has a different approach inside the sphere and outside the sphere. That will be these two integrals. So after calculations of these two integrals we have this result, and the speed will be this expression, which is answer for question 3. Part B. Here we have to find what are xi and n in this expression for power. And here we have to use a dimensional analysis. Let's do this. Dimension for power equal mass multiplied by length square and time power -3. Dimension for xi, it's q power alpha, c power beta, and epsilon 0 power gamma. For q and c, that's easy to count what is the dimension, but for epsilon 0 we have to use this formula to find what is the dimension for epsilon 0. From this equation we can find what is dimension for epsilon 0. That will be this expression, charge square multiplied by mass power -1, length -3, and time +2. And now we can do equations for these powers. So for dimensions, finally we have this equation. We converted acceleration to L power n, time power -2n. From here we can find for masses immediately that gamma equal -1. Also for charge we have alpha plus 2 gamma equal 0. It means that alpha equal 2. For length we have this expression, 2 equal beta -3 gamma plus n, and for time we have -3 equal negative beta plus gamma minus 2n. Here we already know that gamma equal -1, and we have beta plus n equal -1 and beta plus 2n equal 1. It means that n equal 2 and beta equal -3. Finally, we have this result. Xi equal q square over epsilon 0 c cube and n equal 2. And power will be this expression. So that's the answer for part B. Part C. Consider the electron in the first part, except now take into account radiation. Assume that the orbit remains circular and the orbital radius r changes by an amount delta r much less than small r. First question. Consider a circular orbit for the electron where r less than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of r, small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. So here we already know how to count what is the power of radiation. We have power equal this expression. We have to count what is the acceleration and what is period. Period was this one, and acceleration equal to v square over r. And we already counted what is velocity. Velocity was this one. Now we can count what is total energy lost by electron for one period. We have a total energy loss equal power multiplied by period. Period we already counted before, and power is this one. Acceleration it's v square over r, and v is this one. We already counted in previous topics. When we insert everything in this formula, we finally get this formula. But from other hand, we have energy equal kinetic energy plus potential energy. Or we have v square, this one from here, and this is the formula for full energy. And we can write what is the change of this energy when we change radius by delta r. That will be this expression plus force. Force we can count in previous section, and finally we have this expression, and that's equal to our previous expression for delta E, this one. And from these two formulas we can find what is delta R. That will be this part divided by this part, which is this expression. That's the answer for question 1 in part C. Question 2. Now consider a circular orbit for the electron where small r greater than big R. Solution. We still have power equal this expression, but now we have different approaches for speed and acceleration. For period we had this expression, for speed we had this expression, and for acceleration we can count. Acceleration was this one. Now we can count what is the total energy lost for one period. So we have total energy loss equal power multiplied by period. Power is this one, period is this one. Acceleration we can count from here, that's this one. And finally we have this expression for energy loss. And again, from other hand, we have energy equal to kinetic energy plus potential energy. And the change of energy equal this expression, which is this one. And finally, when we equalize this delta E to this delta E, we have for delta R this expression, which is answer for question 2. So we did all answers for all questions and all parts of this problem.